Hello students, welcome to another session of problem solving in calculus. Today we will be working on evaluating limits using the laws of limits. On this file you will see questions with answer options and also the answer at the end for almost all questions, and that is intended for your practice. When we go through these problems, I will solve every new type of problem. And when we come across a problem that has been solved before, a similar type has been solved before, I will ask you to practice that on your own, and you will have the answer key so that you can check your work after you solve the problem. Okay, let us begin. The first problem here is evaluating the limit as x approaches 1 for the function x plus 5 cubed times x square minus 7. Now, I will be talking about the corresponding properties from the limit laws that you watched in the previous video, so you can recall as we do it. This is a polynomial. Okay, so simple law was, one of the laws was, if it is a polynomial or a rational function, as long as the point is in the domain, the value of the limit is the value of the function. For polynomial, the domain is all real numbers. Okay, so in this case you would simply evaluate the function. So that would be 1 plus 5, 6 cubed times 1 minus 7, which would be negative 6. So basically negative 6 to the power 4 if you try to simplify that. Okay, and turns out that value is negative 1296. I did not know that. I knew that 6 cube is 216 times 6 makes sense. Okay, 1200, and then 16 times 6 is 96. Okay, next, the function f of x is bounded by 1 below and x square plus 7x plus 7 above. Right, we use that language. Okay, it's bounded between these two other functions, and we have to evaluate the limit as x approaches negative 1. So first let us check what are the limits of these binding functions at that point, right? And I will want you to be thinking what's the theorem we are going to use here in the meantime. Okay, if we take the constant function 1, of course its value at everywhere is 1, its limit is 1. If you take the other function, which is x square plus 7x plus 7, now that is a polynomial, so you can plug in to evaluate its limit, and then you see that minus 7 plus 7 will cancel and the result will be again 1. So if the functions on both sides, the binding functions, they go to the same limit 1, then the function which has been squeezed should have the same limit, right? We're using the squeeze theorem here. So I will say, by squeeze theorem, limit of the function f of x as x approaches negative 1 is equal to 1. That's the answer. Okay, moving on. Another type now. Okay, and this is now a rational function, and typically when you encounter that kind of question you tend to think, do I have to factor it? And here I will remind you, always do the direct substitution test first. I call it direct substitution test. Okay, that is because if the value is already a finite number, you would have wasted your time trying to factorize and cancel, right? Only when you get 0 divided by 0 or any such situation where it is not a finite number, you need to do something else. So the theorem, again referring to the nodes, as long as the function has a finite value at a point and is a continuous function, the limit is the value of the function. Okay. Now this is a rational function. The question is it in the denominator? So is it in the domain of the function? That I will know if I plug in. So let us see. It will be 5 plus 3 divided by 25 minus 3 times 5 will be 15 plus 5. And turns out that is 8 in the numerator and 30 minus 15, 15 in the denominator. No need to do anything. Okay. Only values which are not in the domain would be where the denominator is 0. Okay. When that happens, we will see what to do later on in those problems. Okay. Next. Okay. So we immediately have the situation now. As x approaches to 2, you can check that x minus 2 will be 0. Now we have a problem. Okay. So what we do first? Still, we do the substitution and show that step. Okay. So what you do is substituting. Now I'm showing you here work that you should write in a written exam. Okay. Substituting x equals to gives. Okay. What does it give? If you plug in 2 there, 2 square minus 2 minus 2. That will be 4 minus 2 divided by 2 minus 2, which is 0 divided by 0 form. Okay. Now that is a indeterminate form. You know, the word indeterminate form, you can use that word. Okay. So what we must do? We must try to rewrite it. Okay. So the next step would be rewriting. Now you rewrite. And how would you rewrite? Limit as x approaches to of that function will be x plus 1 times x minus 2. Now that is factoring. Okay. In algebra, uh, if you need help with factoring, you might reach out to me. Okay. If I'm teaching this course to you, or you can check like YouTube videos on factoring quadratic expressions. Search that. Okay. And learn how to do this factoring. In my college algebra course, somewhere I might have discussed that, but I don't remember. If you want to look at my videos, you can, in college algebra course, you can look for the lesson where we do simplification or rationalization, that kind of work. Okay. Um, but you do that search. Okay. Here we factored. Okay, the process for this kind of function is try to see if you can factor it, and if you are able to factor, you will typically find that the factor that makes it 0 by 0 will get cancelled. Okay, and once that is cancelled, now we are using one more result from the limits, right? What it said was, as long as the values of the function are equal, except possibly at that point itself. So this function has the same value as x plus 1 except at 2, right? And if that is the case, then the limits would be the same. Okay, that was the result we discussed there. So because the point is when x approaches 2, again x approaches 2 means x is not equal to. Okay, so you can go ahead and cancel that and use this result, and now you plug in 2, that becomes 3. You might be thinking here, okay, we're saying x is not equal to 2 and that's why we're canceling it and then we are substituting x equals 2. Are we not, you know, contradicting ourselves? The point is this. When I substitute x here at the end, I'm not saying that's the value of the function. I'm saying that is where the function is going to. Okay, you have to understand the substitution from that point of view. It is tending to that value. It's not equal to that value. Okay, so the answer is 3. Another type. If you now plug in 0, you can immediately see it will be under root 13 minus under root 13 divided by 0. So that will be 0 divided by 0. Okay. So this time I will not write the full sentence. I will just say 0 divided by 0 form. Indirect substitution. Okay. So what we start with? We start with rewriting. Now, when we had a rational function like that, I said that, the best way to rewrite is factorizing. Okay. And when you have radical functions here, okay, these are functions with a radical. If we have root functions or root functions, if you have a radical or a root function, and especially of this type, root a minus root b, the method of rewriting would be rationalization. Okay, so you will be doing limit as x approaches 0. Don't forget to write that. Okay, you cannot just do the other part without writing that at every step. You keep writing limit x approaches to a, that part until you have made the substitution in the very last or second last step. Okay. So this time here I'm going to multiply this by under root x plus 13 plus under root 13. And if you multiply, you also need to divide. You cannot just do one side. You have to do both numerator and denominator. You might remember this, from your earlier studies. This is called rationalization. And in case you need a refresher, it's very simple. If you have a minus sign here, multiply by a plus sign. Okay, conjugate that is called. And what is the property we are trying to use here? The algebra we are trying to use here is a plus b times a minus b is a square minus b square. That came up in the previous video as well, okay, on the lecture. So a square minus b square here will give you x plus 13 under root x plus 13 squared minus root 13 squared. Okay, a is root x plus 13, b is root 13. In the denominator, nothing like that happens. So you are just multiplying those two. Okay. Now we are almost there because this gets cancelled, the root and the square. And then x plus 13 minus 13. We can cancel that as well. So that leaves you with limit x approaches 0, just x in the numerator and x on root x plus 13 plus root 13 in the denominator. Cancel that. And when you cancel like that, now you have 1, by the way. Okay, you are cancelling by division. So what is left is 1. Let me write that in a different color so it's not confused. Okay. So your answer will be 1 over. Now I'm doing the substitution. Okay. Because you will see that if I substitute now, I will get root 0 plus 13, which is just 13 plus root 13. Right. And that does not become problematic anymore. That would be the first answer you get. but then you realize there is a irrational number in the denominator, so you multiply by itself, root 13. So you have 13 over 13, root 13 over 13 times 2, which is 26. Root 13 over 26 after rationalizing the denominator. Okay, here is your complete solution. I forgot to remind you today, as much as possible, pause the video, solve on your own, and check with me. Okay, like whenever I remember, I will say that, but you also remember it to do on your own every time. In fact, when you watch my problem solving videos. Okay, we have been encountering a new type of problem so far, so I'm continuing solving it. Okay, I will tell you when you when we repeat another type now, and this is a trigonometric stuff. Okay, and check what happens with direct substitution. Direct substitution. Okay, h equal to 0 if you plug in cot pi over 4 is 1, tan pi over 4 is 1, reciprocal of tan is cot, right? So it's also 1 minus 1 divided by h. When you substitute 0, you get 0 there. So that is 0 divided by 0. Again, that's an indeterminate form. Okay, so the direct substitution is not helping. We need to do something else. What can I do? Okay, with trigonometric limits, you can try playing around a similar idea of rationalization. Maybe what I'm thinking, this is cot. If you can somehow convert it to tangent, will that help? That will be 1 minus tan over tan. Tan pi over 4 is 1. That's okay. And okay, no, not tan. We will convert it to sine and cos, or cot square minus 1 will not help. Cos over sine. You also think with me for a while. Okay, if I have to think too much, I'll pause the video and I'll come to the solution. Cos over sine will do cos minus sine over cos sine. How will cos minus sine help me? Each of them exists. Okay, but the problem is, one term is also not helping. Okay, so it's not that I'm not having some ideas. I have some ideas, but I'm trying to think, what would be a simple way for you here. Okay. Um, okay. Instead of taking too much of your time, I will go with the thought that I have at the moment, and pretty sure it will work out. Okay, let's see. Limit as h approaches 0, we will, there are formulas for the expansion of cot a plus b itself. Okay, there is a formula for that. And I remember correctly, and it is a fun thing, you might just want to write it for your interest. Okay, we'll probably not take this path, but I'm just telling you, in trigonometry you might have also studied. If you took the course with me, you definitely have studied this. Okay, there is a formula like this. Okay, cot A plus B will be cot A cot B minus 1 over cot A plus cot B. Okay, tan A plus B is tan A plus tan B over 1 minus tan A tan B. Yes. Okay. So the reciprocal of that. So there is a formula like this. Um, you can use that and try to simplify here. Okay, because cot pi over 4 will be 1. Okay, actually I was thinking I will not use it, but looks like it might make our work easier. I'll go with that. Okay, but let me just double confirm the formula before I actually use it. Okay, so I'm glad that actually I tested it because I could show it to you here. And if you already knew, it's great. If not, here's a small derivation of that formula. And my formula, I was right. Okay, just wanted to check. I put it in the box. You might want to pause and see. I definitely recommend do that. It's a very good exercise. Trigonometry is very helpful in calculus. Okay, if you are good at trigonometry, it will go a long way. Okay, so applying that formula here, it will be cot pi over 4 cot h minus 1, right? Cot A cot B minus 1, and there is another minus 1 anyway, over. Okay. Oh, sorry, I should be careful here. That second minus 1 should be here. Okay. Over cot pi over 4 plus cot h. That is just that cot pi over 4 plus h expanded within the numerator. Okay. And you have this entire thing divided by h. Now you need to simplify that. There's some work to do here. Okay. In the simplification process, let me first substitute the value of cot pi over 4 as 1. Then we will do other works. Okay. That will make our work easier. This is 1. Okay. Because cot pi over 4 is 1, that is going to become cot h minus 1 divided by 1 plus cot h minus 1 whole divided by h. Okay. Now I will continue on this side. That equals from here. Okay. That equals, I keep writing limit x tends to 0. Now take the common denominator in the numerator. Okay. So that will be cot h minus 1 minus 1 minus cot h. Basically, when you take common denominator, I'll just show the step here. This 1 here would be replaced by 1 plus cot h over 1 plus cot h. Right? We multiply numerator and denominator by 1 plus cot h, so say they have the same denominator. Now you can just work with the numerator, and it's cot h minus, and there's a minus sign in the middle here, so you get minus 1 minus cot h whole divided by h times 1 plus cot h. Okay, and so cot h and cot h cancels there. You get negative 2 divided by h times 1 plus cot h. Okay, which is looking good so far, except that I'm thinking again. Tan h. What's the point of doing tan h here? Tan h over h will be 1. and 1 plus tan x. Okay, it should get a finite answer. Okay, and let me check the answer here. Yes, the answer is a finite number. So I want to make sure that we don't mess it up before we get the final answer. Okay. Now at this point of time, you'll notice that if you simply plug in h as 0 here, you are going to get minus 2 divided by 0. Again, there is a problem here. Okay. So we don't want to do that. We want, no, h was going to 0 or 0. Yes. Okay. So we will try to see if we can simplify it. And the simplification is like this. This is going to be limit h approaches 0, negative 2 over h. And now you convert to tan. Okay. And I'll explain to you in a second why do we convert it to tan. That will be limit h approaches 0, negative 2. This tan h from the denominator of the denominator will flip and go up. You will have h times tan h plus 1 here. Okay, finally we're done. We are going to use what is called the product rules of limit here. That gives you limit h approaches 0, and you can separate the two things. Tan h over h, that's one part, and then limit h approaches 0, negative 2 over tan h plus 1 is another part. Okay. And now just like sin h over h is 1, this tan h over h is 1. I want to finish this problem and then I'll come to that. Okay. And on the other side, if you plug in h equal to 0, you get negative 2 over 0 plus 1. So the whole thing, if you simplify, becomes negative 2, which we checked was the answer. Okay. So let me zoom out actually, and show you the whole solution there. Okay. Follow it, every step of it, and make sure you understand the algebra. So sometimes, limit calculations can involve work. Okay. I don't know. I would also recommend do a Google search, put this question to AI, and there might be a better way or shorter way to do it. My approach, and which is what I am trying to teach you also here, is we are trying to learn here. We just don't want to get the solution. So sometimes, if you are especially, let's say, in an exam situation, when you have to solve a problem, you may not be able to think of the most efficient solution at the time, right? Whatever, based on your knowledge and the formulas and the techniques that you will have to go ahead and do that solution, on the spot. So that's what I'm doing here. Okay. Um, this may not be the most efficient, could be, okay, or may not be, but at least in the process we applied what we had learned, and I could get a chance to review, some algebra rules here. So yes, it's always useful. Okay. I was saying I will talk to you about this part here. Okay. That result we have not seen explicitly, but it's not very difficult because we talked about this earlier, right? Limit x approaches to 0 of sin x over x is 1. That's one of the results we use. Now, it came up in one of the lectures. If you take that and apply here, limit x approaches 0, tan x is sin x over cos x, right? And then there is x in the denominator. Now think of this. I'll just write directly here, you'll understand. Split this into two things, sin x over x and 1 over cos x. So the sin x over x is 1 by the result that we wrote just above it. And then 1 over cos x, if you plug in 0, you are doing 1 over cos 0. And then recall from trigonometry that cos 0 is 1, 1 over 1. So after all, everything becomes 1. Okay. So limit as x approaches 0, tan x over x is also 1. And hence we solve that. Very interesting problem, I would say. Okay. And here is your another problem on, you guess which theorem. Okay. I let it I let you do it as a practice. We did a similar problem previously in the video if you want to check. Okay. Next, the limit that you are seeing here, again, hope you remember it from pre-calculus or college algebra class. This is called the difference quotient, right? And it is taught separately. I remember, in most courses as a standalone topic. And many times students ask, why are we doing it? Like it's a unique, separate thing we study. Okay. And anybody asks me that in pre-cal or college algebra, I tell them it comes up when you do calculus. Okay. It also comes up in other contexts, by the way, in some real world applications also. But in calculus, it's super important. Okay. Why? Because this is how very soon you will see the derivative is defined. Okay. In fact, what you are doing here is exactly the derivative of the function at x, f prime of x. This expression is the derivative. Okay. Of what? The function f of x is x to the 6. Okay. If the function is x to the 6, this would be the expression for the derivative of the function. Okay. So the derivative itself is a limit. You are getting a introduction to it. Uh, what you call advanced introduction, a trailer. Okay. Let us evaluate this limit. Right. As before, if you plug in h equal to 0, you will get x to the 6 minus x to the 6 divided by 0, which will be 0 divided by 0. And we always mention that when you have to do such a work. Okay. So you say that 0 divided by 0 form. Indirect substitution. So we need to do something else, right? And that something else would be expanding that. Now, expanding the power 6, you can do using what is called binomial theorem, if you have studied it in some context. Okay, like we expand a minus b whole squared, you can expand a minus b to the power 6. But I will not do that path because it will be, maybe I'm assuming most of you have not done it. We can do what we have already done before, and that is factoring, as always. Okay, so let us factor it. It can be, the 6 is 3 times 2, right? So you can think of that as x minus h whole cubed. Okay, so that would be x minus h whole cubed minus x cubed squared, sorry, times x minus h whole cubed plus x cubed, a minus b times a plus b. Okay, and now if you split it, now I skipped that step, one step there. I hope you got my point. Okay, let me just write it here. I was doing this. It's x minus h whole cubed square, minus x cubed square. So it's like a square minus b square. And we did here a minus b times a plus b. Okay. And then you see that if there is a plus sign, there is no harm in substituting x equal to 0. It will be x cube plus x cube. So in order to do that, we will split this limit into two components by using the product law, right? It allows you to split the limit as long as both limits exist. And we will show that they exist in fact later. Okay. So far so good. The second part, the second limit here, you don't have to worry. Let's focus on the left side. Again, if you plug in h equal to 0, it will be 0 minus, sorry, x cube minus x cube over h, right? So this time you have to use a minus b whole cube formula. And that you should know. Okay. There are two formulas you could use here. I will write them on top here. You could either go with a minus b whole cubed formula and expand this here, or you could factor this whole thing by using a cubed minus b cubed factoring formula. Okay, anything is fine. I will go with the first one, expanding that expression by a minus b whole cube. And the formula for that, you should be knowing it. In case you don't know it, I'm going to write here. Please write it down. And this should be something in your note-taking guides, notes, like if you that you use in the exams. Okay. A minus b whole cubed is a cubed minus 3a square b plus 3a b squared minus b cubed. Okay. A very nice pattern to remember. So this, the left side would be limit x tends to 0 of x cubed. We're going to use that now. Okay, 3x square h plus 3x squared minus x cubed minus x cubed whole over h. Okay, that last minus x cubed is this second part, but before that is that a minus b whole cubed formula. And then this is the left limit. The right side limit is if you plug in 0 now, you just get x cubed plus x cubed. Okay. So in the next step, that 2x cubed, this part which got simplified, I wrote front here. Okay, that is 2x cubed. And then let's look at the limit, which has not yet been completed. Limit h tends to 0. Now let's focus here. Okay, what's going on within that? Within that, you can cancel the x cube with x cube. And then you notice that every other term has an h in it, right? And I'm pausing here and I want you to really remember that, because that's how most, no, almost every derivative calculation will work. Okay, that is called finding the derivative by a fundamental principle. Okay, we will talk about them. But this is what always happens. You will end up getting an expression where h is a common factor in all the terms, which makes it possible to find the limit, because you can now factor out that h and cancel with the h denominator, right? So what will remain? Out from h square, you cancel, one h remains. From h cubed, you cancel the one h and you are left with h square remaining. Okay. So the expression would be now minus 3x square minus 3x h minus h squared. Check your algebra carefully there. Okay. Pause if necessary, write on your own, and make sure you follow every step of the calculation. Okay. And Then you can plug in 0 now because there is no more denominator. Now if you plug in x equal to 0, you will get minus 3x square only. The other two terms will become 0. So overall it becomes minus 6 x to the 5. Okay. Where did we get that minus sign from? Yeah, okay. I think should not have got a minus sign is what I'm thinking. Oh no, okay, minus sign is, it seems correct. So looks like this was not x to the 6. We're doing the derivative of x to the minus x to the 6. Anyways, okay. So that's your answer. All right. Again, I zoom out, check your work carefully. Okay, moving on. All right. Next question, luckily, is simple. It says the left limit is 3.7. X approaches 3 from the left. Okay. And you are given the information that the limit of the function exists. What is its value? I'm sure you are able to answer immediately. It's the same. If the limit exists, it's the same as the left limit and the right limit. Okay. So by saying the limit exists, what the question is telling you is the right hand limit also exists and its value is also 3.7, and that is why the limit exists. Okay. And it must be the same value. Moving on. This is a repetition, okay, of a similar problem we have done before. Please check it out. You see what happens if you try to plug in directly, and then you might have to do some work, to simplify, and then after you do the cancellation, you will get your answer. Please practice. Okay. Next, another very interesting question. You might want to be very attentive to this. Okay, it is a one of a kind question here. It is about what is called a greatest integer function. Okay, what is that function? Typically, there should have been a dot here. I think I should have remembered to put that while typing it. So that symbol, dot means whatever input inside that is called the greatest integer function. What does it do? Here's the definition. If you take the greatest integer function or greatest integer function value of any number, you have to find the integer number, which is just small than that. Greatest integer less than that number. Okay, so the output would be an integer value which is closest to it, but less than it, on the left side. Closest to it on the left side if you look at it on a number line. Now, if that is the function, find these limits is the question. What we will do is not just find these limits, because it's a very interesting function and important function also. We will try to see if we can sketch its graph. Okay. Let us see, starting from 0 to 1, let's say. Okay. What the function is telling you is, if you are at, let's say, 0 0.5, 0.5 here, the value of the function would be the greatest integer, which is less than 0.5. And then you will think, okay, that's 0. But 0 is also the greatest integer if you are at 0.6. You see immediately what is happening is From starting from 0 up until 1, I'll zoom in, all values, all of them will get mapped to 0. That's the integer just before them, right? But when you reach 1, you have to make a hole here. Okay, open circle, because at 1, the integer equal or less than, see, it's a definition, okay, equal or less than. So the integer equal or less than 1 is 1. So the output of 1 will be 1. And I don't know if I showed the circle to be big enough here. I'm just going to artificially make it bigger here, so you see that it's an open circle there. At 1, the value will be 1. And that will continue for 1.1, 1.2, 1.3. For all of them, the integer less than that, and the largest one is 1 until, until you reach 2. At 2, you will have to jump to 2, continue, and so on, right? That's on the right side. Similarly, on the left side, let's say you are at negative zero point 0.1 or zero point 0.5. What is the greatest integer less than that? You will have to go to the negative 1. So nothing different actually. It's the same pattern that will continue. So up until you reach 0, all of them will get mapped to negative 1. Exactly at 0, it will jump to 0 and then continue. So if this is negative 2 here, and let's say negative 2 here, negative 1 here on the axis, then from between negative 1 and negative 2, it will be there. So you see this ladder, this staircase, these kind of functions are called step functions, right? Which are like steps. Okay, that's a graph of the greatest integer function. Okay, let us now apply that to these limits. As x approaches 1.5, now the limit becomes interesting. Okay, when you approach from the value 1.5, my bad, 1.5 is here. Okay, this is 1.5. Now as you approach 1.5, either from the left or from the right, up here, your output is 1. Okay, understand that. So when you say you approach 1.5, in the language of limits, you must be really close to 1.5. It's not that you can be at 2 or 2.5 and say that I'm still approaching 1.5. Yes, that's fine, you are approaching, but to consider for limit evaluation, you have to get more close. Okay, more close, more close. There is no into it. So definitely you have to be between 1 and 2. And when you're between 1 and 2, your output is constant. That's 1. Hence, that limit is just 1. Alright. Similarly, you can check now. If you are at negative 1.5, you can go down and see, all of them get mapped to between negative 1 and 2, negative 2, they are mapped to negative 2. So this is negative 2. Okay. But what if you are approaching 1? And look at the graph. When you are approaching 1, now there is a different game. If you approach from the left side, these values are supposed to be 0.5 and 0.6. Okay, so I just remove them. This is 0.5 here. If you are approaching from the left, see, as long as you are on the left side of 1, not at 1, on the left side of 1, the values are 0, right? The value of the function is 0. But if you are anywhere on the right side of 1, the value of the function is 1. So for these integer values themselves, what will happen is the left limit will be different, the right limit will be different. X approaches 1 minus, you will get 0 from the left. X approaches 1 plus, you will get 1 from the right. So the overall limit does not exist. Okay, moving on. Find the following limits. This is about absolute value function. Okay. As x approaches 2 from the right and 2 from the left, we have to do 2 of them. Let's look at the right side. When you approach from the right side, x minus 2 will be greater than 0, right? Because x is greater than 2. And when the quantity inside the absolute value bars is greater than 0, then by definition it is equal to that x minus 2 because it is positive. You cancel that and you can easily get the result is 1. But if we approach from the left side, now x minus 2 is, in this case, x minus 2 is less than 1, less than 0. X minus 2 is negative. Okay. If x minus 2 is negative, the absolute value of x minus 2 will have to be negative of x minus 2. Go back to the definition of absolute value function if you need and think about it. Okay. The quantity inside the absolute value sign here is x minus 2. So when x minus 2 is negative, we put a negative sign here. That is clearly negative 1 because you could cancel that. What is left is negative 1. So the answer is 1 and minus 1. Okay, it's not the same. Another problem you should be able to solve based on our earlier discussions. And remember always, whenever you are evaluating limits, do the direct substitution first. Okay, and check. Only if you have a problem with direct substitution by getting an under root negative quantity or a 0 in the denominator or any such issue, until that point, if that doesn't happen, the value of the function is your answer. Okay. Here, another very interesting problem. We are evaluating the limit from the left. Okay, that's one thing I want you to note. The second thing I want you to note is if you do direct substitution, when you plug in 4, okay, see now whether even if we are doing one-sided limit, when it comes to substitution, you substitute the value of the x wherever it is approaching. Okay, um, it's not different for limits and one-sided limits. The process is the same. You plug in there, you will get, of course, like 16 minus 16 when you plug in x equals 4 and divided by 16 minus 32 plus 16, and that will be 0 divided by 0, which is indeterminate. Okay, so what we should do? Some rewriting and rewriting is going to start like this. Okay. You see they are rational functions. So try the factorization. That will be limit as x approaches 4 from the left. In the numerator, x square minus 4x. Relatively easy factoring. X is common for both of them. Denominator is a quadratic. Again, I was talking earlier about quadratic factoring method. You can check that it is x minus 4 whole squared in fact. Okay, x minus 4, x minus 4. The sum is 8, 4 plus 4, 8, and the product is 16, right? 4 times 4, 16. Okay, and because as x approaches 4, x is not equal to 4, you would go ahead and cancel that. But even after cancellation, the problem is this. Okay, previously we did problems where you could cancel that and you would be fine after that when you substitute. Now you try to substitute 4, you get 4 divided by still 4 minus 4, right? Okay, but the difference now is 0 is in the denominator only. Okay, so what I will do is I will not write 4 minus 4, I will write 4 this minus sign here because x is approaching 4 from the left. Okay, we'll remember that and we'll write in 4 minus here in place of x. What that means is this will be 4 divided by 0, but a negative 0, what we call a 0 less than 0. Okay, like negative 0.000001, that kind of number. Okay, so this is a distinction we have to make. In limits, as we said, x is tending to 4, not equal to 4. So the values of x are a little less than 4. That is indicated by 4 minus. But when you subtract 4 from values little less than 4, you are going to get something very close to 0 but negative, right? That's what 0 minus refers to. We call it negative 0. Okay, sounds contradictory, but that is the meaning of it, negative 0. Okay, now you have 4 divided by a negative very, very small number. That will be negative infinity, right? That's important. You see, so when it is not defined, when it is not a finite number, we try to see if it is plus infinity or minus infinity. We want to be as accurate as possible. If it was 0 divided by 0, it would have been indeterminate. Please understand here. It is not 0 divided by 0. This is 4 divided by 0. That is undefined but not indeterminate. Okay. And the particular undefined here is it is negative infinity. And you see that's your answer. Again, I said this is a very important category of type of problem. Think again, do similar problems for more practice. Okay, next. At this point, it is almost routine. This is something we have done before. Okay, if we plug in, but I will still discuss because of the type of formula we have to use here. If you plug in t equals 4, you see that it will become 0 divided by 0. Not difficult to understand that. Okay, so what you do, rewrite. And the rewriting always, because it is a rational function, you are going to go with factoring. Just that you need to know the formula for factoring. Numerator, I'm sure you know it. Just go ahead and write a minus b, a plus b. The denominator is what will might be a new formula for you. Okay. I hope it's not. in your high school, you might have studied this. A cube minus B cubed. If you did not, please write it now and remember it. Very interesting pattern. It's not plus 2ab, okay, it's plus ab. Be careful there. And all of them are plus plus plus. The minus sign is here, a minus b. That's a factoring formula, okay. And if you apply that factorization here, it will be t minus 4. By the way, knowledge of small tables is important. 64 is 4 cubed. 4 square is 16. 16 times 4 is 64. Okay. So it's t cubed minus 4 cubed. And when you do that, it's t minus 4, t square plus 4t plus 16. Right? A square plus ab plus b square. And then you see that t minus 4 cancels. Because t is approaching 4, t is not equal to 4. And after you do the cancellation, you try to substitute here t equal to 4. Now you get 8 divided by 8 plus 16, not 8, 16 plus 16 plus 16, which will be 48. So 8 divided by 48 is 1 over 6. Okay, and you can see that here. Fine. Number 17 you can do, it's a simple one. Number 18 is the derivative thing that I was saying earlier. Okay, the difference function, right? So this would be, by the way, I'll write the notation, a little different derivative than the before, but still derivative. Okay. The way you will work with you, I want you to practice it. Okay, I'll leave it to you, but I will show you the first step. First, you write it in fraction form. That will make your work easier. Okay, that's 1 over x function. So 1 over 3 plus x minus 1 over 3 over x. Okay, so what is the derivative we are evaluating here? Here we are evaluating the derivative of a function at 3, because you are taking a difference from 3 plus something, right? And the original value is 3 here. Okay, so you are calculating the derivative at 3. So it will be f prime of 3 in the language of derivatives. And anyway, that is the future, but good to know. Continue. Okay, do the algebra simplification. Remember, you should be able to cancel this x in the denominator with the numerator after your simplification, and that's when you can plug in and you'll get your answer. Okay, since I talked about derivative, you know which previous problem I said you can refer to. If you are stuck somewhere, you can go back to that problem and see what we did there. Okay, moving on. This is a direct question, you can do it. We just no, this is also direct, simple enough. Let's look at 21. Another step function. Okay, previously we talked about the greatest integer function, right? Oh, sorry, not step function, piecewise function. My bad. Greatest integer function also was piecewise function, but of a special type. This is a general piecewise function. And what are you being asked? You are asked the values of a for which the limit exists. Okay, and a very good understanding of functions is going to come here. We said previously that as long as it's a a rational function or a polynomial function, or I said any elementary function, it's defined uh, when you look at its domain, it will have its limit and it will be continuous there, in fact, right? So in that sense, the 2 minus x, all of these are polynomials. All three are polynomials, so there should be no problem in its domain. Okay. So for all the values of x less than -1, it will be continuous. And so the limit will exist. You see that in the answer here, so all values less than 1, it exists. Between 1 and 2, again, the rule is x. And what you have to understand is this, okay? There's one more concept hidden here, which is as long as you are less than -1, the formula that we are going to use is 2 minus x. And that 2 minus x is going to be a line like this. Okay, it will be somewhere reaching here at 3. That will be your function. So it's the same function. Now, if you are, let's say, evaluating the limit at -2, on the left and on the right, it's the same rule. That is 2 minus x. Its limit exists. Similarly, if you are anywhere between -1 and 2, the value of the function is x, right? The graph of x um, looks like this. I have to delete that what I wrote -1 there, so I can draw this, okay? The graph of a function, y equals x looks like that, okay? So if you are anywhere between -1 and 2, it's this rule you are going to use from the left and from the right, the same rule. So the value of the function, limit of the function will be the value of the function. So between -1 and 2, also the limits will exist. Similarly, if you are, and this rule goes until less than 2, open circle there, okay? For equal or greater than 2, you have to use the x minus 2 whole squared, whose graph will be like that, or like a parabola, okay, with the vertex at 2, 0, right? Remember again from college algebra, that part, okay? Anyway, the graph will be here. So if you are more than 2, see, not equal to 2, but greater than 2, you will be using the same rule on both sides. So the limit is the value of the function, which is a polynomial, and it exists. So that is also good. Then where is the problem? There are only two potential candidates, and those are exactly where the rule changes. Okay, -1, because there are two places, the left and the right have different rules for -1 and 2. The right side of 2 and the left side of 2, you can see in the graph, they have different rules, right? And actually, I drew the graph here. You can already see the limits are different from the left and right. For all of them, left hand limit and the right hand limit exists, but they are different. Hence, the limit does not exist at those points. And those are missing here. What you should understand from this is, if your function was given in such a way that even though the rules were different, but they met, suppose I'm saying hypothetically, okay? If I gave you another function where the graph on the left was something like that, let's say, and at -1 here, okay, they happen to meet, even though the formulas are different. One is a straight line, one is a parabola, but they met here, suppose. Then the limit would still exist there. In which case, you would not write this. You will say from -infinity all the way till 2 the limit exists, including at -1, because the left and the right limit are the same, right? You get the idea, okay? That is this question. So in summary, you should check for the values where the rule changes. At that point, does the limit exist or not? That is it. Okay. One more question. And this again, you will be able to do based on our work before, except I will just tell you how you would factor x to the 8 minus, 5 to the 8. Okay, according to formula, that's what you have to do here, isn't it? And here's the logic. Not x, let's write it a to the 8 minus b to the 8. You can repeatedly use a square minus b square formula. Okay, this will be a to the 4 minus b to the 4 times a to the 4 plus b to the 4. And in this problem, here you can do the direct substitution. It will not become 0, right? So you split the limit into two parts and focus on a to the 4 minus b to the 4. That would be a square minus b square times a square plus b square. Again, this part you do the direct substitution by splitting the limit using the product rule. We have done that before in this video. Okay, look at some previous problems. And then you focus on here because that would still be 0 divided by 0, because we are subtracting here. And that would be a minus b times a plus b. And here you can do direct substitution. And this will cancel with the denominator finally because you have that x minus 5 in the denominator, right? And your answer would be all these products. That's the outline. Do it. Okay. Next problem. Simple enough. We are evaluating the limit from the right, but we always do the direct substitution first. Remember. Okay. Uh, yeah, you can do it. This one also you can do. Try to do the direct substitution first. Check what happens. Now, if you get 0 divided by 0 or something like that, you might want to do factoring and see what happens next. Okay. Practice. Like the one we did above, x cube, x to the 8 minus 8. This is similar, but the function is now x cubed. So you might want to use the a cubed minus b cubed formula that I talked about few seconds ago. Okay. Okay. Another very interesting problem. Okay. You are approaching 3 from the right and you see that function. Oh, that's looks like one end supposed to be ln. Okay, that's a typo there. That's ln x, natural log. So you think, oh, okay, this involves some natural log, so some, maybe I need some advanced tools here, right? Okay, let's see. It looks like that. Try to evaluate each limit. See, if you have some complicated expression, you can break it down. Okay, you can use the difference rule and say individual component. This one, okay, when you apply that limit, it will be 3 divided by 3 plus minus 3, right? Some quantity little bigger than 3 minus 3. Minus 3 over ln of some quantity little bigger than 3 in the direct substitution. And that is 3 divided by positive 0, similar to the negative 0 we talked about earlier. And this will be basically 3 divided by ln 3. Who cares? Okay. In the limiting case, it's if we simply substitute 3 there won't be any problem. And the thing is, ln 3 is defined. Remember the graph of ln x? It is 1, sorry, the value is 0 at 1, then it is positive value, right? So this is some positive number, okay? whatever is its value, who cares? Because this is plus infinity anyways, minus some finite number, which will not make any difference. So your answer would still be plus infinity. Okay. And that's what you're seeing here. All right. So looks complicated, the function, it might think that, oh, maybe do I have to rationalize? Do I take common denominator? No, do the direct substitution always first. And if it somehow gives you a answer, you're done there. And although I got the answer infinity, you might wonder, see, you did not get a finite number, you got the answer infinity. Why did you not try to mm, simplify or do some rewriting? The reason is you already have only x divided by x minus 3. What are you going to factor? That is a rational function. How am I going to factor it? It's already lowest. So I can see that, there is no rewriting which is going to help here. Okay. And if it was 0 divided by 0, I would have definitely have to find a way to rewrite. But when it is infinity, it's okay. It is an infinite limit. Okay. Um, you can do that. Okay, simple enough. Use the squeeze theorem and do it. Again, answer is given here. Try to come up with your function. It won't be that difficult. Okay. Um, all these complicated expression doesn't matter. That is the beauty of squeeze theorem. Okay. Here you might think, oh, the function is complicated. Is that going to make any difference? No. You are going to squeeze using some simple functions. Okay. And follow what we did in the lecture video about the squeeze. We'll do it or in this problem video also we did that earlier. Okay, try, it should be simple enough. That was a long video, but we did cover some very, very, very important problems. I hope you learned. Practice more, do the homework, you'll be good. Okay, I will see you in the next lecture. Thank you.